And the title of the talk today I'm going to give is the supercritical surface waves generated by a positive forcing. We made some theories and experiments. I'm Choi from Korea University, and this is joint work with Sung-Min Shun and Son in Virginia Polytech Institute, and Hwang, she's a former student of mine, and now she's in Aju University as a postdoc. And these two people are in the Korea Ocean Research and Development Institute in Korean 해양연구소. So for the experiment, I worked with them. Okay, and today my talk is composed like this. First, I'm going to introduce the fluid domain and mathematical formulation. And in the formulation, we have derived the first KdV equation. So first, I'm going to talk about the first KdV equation when it is in a steady state. And the next, I'm going to talk about the time-dependent KdV equation. And after that, I'm going to show you the experimental result, which is consistent with this numerical result. Okay, so the fluid domain is given like this. Here is a rigid bottom, and fluid is flowing over the rigid bottom, and there is obstruction at the bottom. And we assume that the obstruction has a finite support. It has a contact support. And the fluid is coming over with a constant speed, and then it goes over this obstruction. Then some wave will be generated. And this eta x is for the wave. So y star is eta x is the equation for the wave. G is the gravitational acceleration constant, and v star is the function for the obstruction, and h is the depth of this fluid at phi infinity. And here x is the horizontal variable, y is the vertical variable, t is for time, and u is the horizontal speed, and v star is the vertical speed. So u is horizontal speed, v is the vertical speed. Then there are several assumptions. The first one is that the fluid is ideal, so there is no viscosity, and incompressible. So the density is constant and two-dimensional, and so constant density. And we are going to consider this fluid motion only for the case when the speed is near Freud number. And Freud number is defined as this. So c is the speed of the fluid at phi infinity, and then divided by square root of gravitational constant times the depth of this fluid and the square root. And this is a definition of Freud number. And we are going to study the fluid motion only for the case when Freud number is near 1. If the speed is quite different from this Freud number, then linear theory works there. So it's not very interesting. But in this case, we must study the nonlinear theory. Okay, so the Freud number is near 1, but it is close to 1. And the Freud number is now, the f is now near 1. And if f is a little bit less than 1, then the fluid is called the subcritical flow. And is greater than 1, then it is called supercritical flow. And if exactly 1, then it's critical flow. But today's talk, I'm going to talk about this case. So fluid number is greater than 1, slightly, not very much. Okay, then the motion of the fluid is given by these Euler equations and kinematic conditions. The first one is from the conservation of mass, and these two are from the conservation of momentum. And at the free surface, we have this kinematic condition, and assume that the pressure is 0 at the surface, because above the fluid there is just air. And in this equation, because we have piece of x and piece of y only, the pressure is after constant. There's no difference. So you assume that the pressure is 0. Okay, and at the rigid bottom, the fluid is going over the bottom smoothly. So there's no tangential effect, something like that at the bottom. And so all the equations and kinematic conditions. So by solving these equations and boundary conditions, we can explain the motion of the fluid. We can explain the motion of this fluid exactly. But nobody can solve this equation exactly. So we are going to use some method to find the approximation of the solutions of this equation. Okay, for that purpose, we are going to use this dimensionless equations, dimensionless variables. So here epsilon is the ratio, square of the ratio of the horizontal, the vertical length scale and the horizontal length scale, and assume the horizontal length scale is much greater than the vertical length scale. So this epsilon is a kind of parameter. And t is non-dimensionalized, and x is non-dimensionalized like this. So here there is some difference. Okay? Y is just y star divided by h, but x, in the case of x is x star times square root of epsilon divided by h. So there's a kind of difference in the order. This is called the long wave assumption. Now, even though x is quite large, x star is large, x will be not very large. So the horizontal variable is kind of shorter. So it's a long wave assumption. And others are non-dimensionalized like this too. And then using these non-dimensionalized variables, all the equations and kinematic conditions become like this. So we don't have any dimension right now. So we can deal with these equations mathematically. And then to solve this equation, we are going to use asymptotic expansion, so regular perturbation method. So assume that horizontal speed, vertical speed, and pressures, they have this kind of expansions. So zeroth order, first order, and second order of these series, like Taylor series. And this use of U null, V null, and P null is a kind of primary flow. So it's a solution. We may say that U null, V null, and P null are solutions of this fluid when there is no obstruction. So then now U null is the horizontal speed of primary flow, so it's a constant. So originally the flow was moving from the left to the right with constant speed, and there was no vertical speed originally. And the pressure is a function of depth only. So this explains the the situation of the primary flow. And after that, suddenly a bump appeared. So there will be some changes. And this term and this term will explain the changes. Okay, then we put this asymptotic expansion to these equations and boundary conditions. Then there will be zeroth order equation, first order equation, second order equation, etc. Then solve the zeroth order equation, first order equation, and second order equation according to the order of epsilon. Exactly, we can do that. Then after solving those equations, we can come up with this famous equation, which is called forced KDB equation. And all these U1, U sub 1, V sub 1, P sub 1, and U2, V2, P2 are function of this eta. And so by solving this equation, we can find U2, V2, P2, U1, V1, P1, and everything. So we can explain the motion of the fluid totally. So by solving this equation, we can explain the fluid flow. Okay, so this equation is quite famous. Most of the people in fluid area knows this equation. And but still, there are many things to be done in this equation. Even though this equation looks so simple, but still, many people work on this problem, this equation. Okay, so this is PDE equation with forcing term. And this Bx is from the equation of bottom, which is the bottom. And we have this. So first, here, somewhere here is lambda. I think I should explain this lambda. And lambda is this. So at phi infinity, u is 1 plus epsilon lambda. So this lambda is kind of u1, u sub 1 and negative infinity. At the primary flow, u naught was 1. And now it is perturbed a little bit. And this epsilon times lambda at phi infinity. And this lambda is u sub 1 at negative infinity. And it appears at here, in front of eta x term. Okay. So first, the stationary case. So the case when this eta x disappears. So it's a kind of the case when case long time later. So the flow at the suddenly we think like this. The primary flow was flowing like this, flowing, and suddenly a bump appeared at the bottom. Then there will be a kind of transition period. After a long time, everything will be stabilized. So after a long time. So it's without this one means after quite a while, the fluid will be like this, and so steady state case. And then because we don't have this term, all terms have x derivative. We can integrate first, and then the equation becomes simple. And boundary conditions are given like this. So there's no there's no elevation at plus at or minus infinity. So fluid is just very calm at plus at minus infinity, and then the equation becomes like this. Okay, and we have shown we are going to study the case when lambda is positive only. So here this lambda is positive. So u has a perturbation, and the perturbation is positive. Then if there is no Bx, then this will become 0. Then immediately you can find two solutions. One is 0 and the other is like this. 0 is just obvious, and this solution is called the solitary wave. There are two solutions. One is 0 and the other is solitary wave solution. And now bump appeared. Bx is not 0. Then first we can prove several facts, because now it's an ODE problem, so it's quite easy to prove several properties. And the first one is that if the lambda is greater than this number, then there is a unique solution. Now eta is surface elevation. There are two etas. One is small and the other is large. Well, there's a misprint. One is small and the other is large. So if lambda is greater than this number, then there is a small solution which is near 0. And there's another lambda, and if another critical lambda, and if the lambda is greater than that critical number, then there is a solution which is near this solitary wave. So one is near 0 and the other is near this solitary wave. So there are two solutions. And the smaller one appears if lambda is this one, and the greater one appears if lambda is greater than some number. And another thing is that there is a constant lambda, that if this lambda is less than that critical number, then there's no steady solution which goes to 0 at infinity. So it's like this. This is the lambda axis, and it's greater than 0. There's some critical lambda here. If this lambda is less than this critical number, then there's no steady solution which goes to 0 at positive infinity. So in fact, there is no steady state in fact in between 0 and this number. And if lambda is greater than this, there are two types of solitary wave solutions. There are two types of steady state solutions. One is near 0, and the other is near solitary wave. So one is small, and the other is large. Okay, so we try to find those solutions. And as an example, the case when the bump is given by this square root of 1 minus x squared, so half circle, and times the r. Then for different r, there are different lambda exist. So if in the case when r is 1, so bx is square root of 1 minus x squared, in that case, it's a bridge curve. So if lambda is greater than this number, 1.40 something, then there are two types of solutions. One is near 0, and the other is near solitary wave. And if lambda is less than this one, there is no such solution. So there is no steady state in fact. And now here's an example. Lambda is 1.5, somewhere here. There are two solutions, and the smaller one and larger one. The smaller one is this, and the larger one is this. So there are two types of steady state solutions. Okay, and then time dependent case. We first thought about well-posedness, and it worked quite well. If the initial value is given in H1, then the solution is well posed. And we could prove one more thing, that if lambda is greater than 0, and there are two types of solutions. One is small and the other is large. And this smaller one, eta Sx, which is smaller one, and then we could prove that that is stable. This one is stable. And after that, we use the numerical method to check to see the kind of behavior of solutions for different initial data. So the first one is the case when the initial value is given by this small solution, and it's quite stable, no change at all. When the time is t is 19.5, so quite a while later, still the shape of the initial value didn't change at all the same. But the case of the greater one, larger one, it was not stable. I have used the greater one as the initial value, and then immediately one solitary wave came out, and then the small steady state solution appeared. So long time later, this goes out from the domain, and this small solution remains on. So let me show you a movie. 어떻게 해요? 아니, 그걸로 안 나가고 지금 거기서 여기서 두 번. Okay, so the larger steady state solution was given as the initial value, and then the solitary wave appears and it moves to the left, and this small solution remains. So we can say this greater one became the smaller one long time later. Okay, so the case when we give positive error, positive noise to the greater solution, the solitary wave appeared and it moved to the left. And the case that the noise is negative, the solitary wave appears and it moves to the right. So it depends on the sign of the noise. If the sign of noise is positive, then the solitary wave appears and moves to the left. And if it is negative, then the solitary wave moves to the right. So the case that the initial value has a negative 10% of noise, then the t is 19.5. The solitary wave is somewhere here. Okay, and I use the initial value 0. So the 0 is used as the initial value. So you may think like this. The primary flow was flowing with constant speed and suddenly bump appeared. Then the bump will generate some waves. It's that situation. This is that situation. Then if lambda is 3, so this lambda is 3, then just small wave appears and then it remains, just no change at all. Small wave appears and then there's no change. But the case that lambda is 0.5, something different happens. The trail of solitary waves appears here, and here is a mass compensation. So this agrees with this result. Here we have proved that if lambda is less than some number, then there is no stability, no steady state. So if now this is the case when lambda is 0.5, then there is no steady state solution, because the solitary wave is generated repeatedly. And if lambda is greater than some number, then it is just stable. So it's coincide with this theoretical result. Okay, so now this is the case when lambda is 0.5. So the solitary wave will be generated repeatedly. The wave looks very sharp, but in fact it is not, because here this is like 10 or 20. That is from here it is 0 and it is about 20 or 30. We don't have number here, but this looks very sharp, but in fact it's not. It's very smooth. The height is quite less than the width. Okay. And the case that lambda is 0.95, we don't have such phenomena. And if lambda is 0.94, we have less phenomena. So the critical lambda is in between this 0.94 and 0.95. So if lambda is greater than 0.945, something like that, then we have this phenomenon. And if lambda is less than this number, 0.945, so that's this interval, then the trail of solitary wave appears. So there's no steady state in this case. Okay, and we considered the case that the traveling solitary wave was given as initial value. It's kind of interesting to see this kind of phenomenon. So we have checked it. And solitary wave solution, solitary wave is given like this. Here C is the speed of the solitary wave, here is the C, and x0 is the phase shift. And here's the, what is that? This is the size of the solitary wave, 2 lambda minus C. So for different C, we have the different height. And for different C, we have the different speed. So, and the C is small, then C is, if the height is small, then that has the greater speed. Okay, and something interesting appeared. Something interesting has appeared here. Now, here C is 1.5, so the speed is less than this speed. 1.9. The solitary wave has the speed of 1.9 here, and the solitary wave has the speed of 2 in this case. This case, solitary wave comes from the left and the right, and then here is a bump, and it is bounced at this position. So the bump, the solitary wave is reflected because of this bump. Now this is the case that C is 2, so slightly faster than this solitary wave. Then this case, the solitary wave comes and then goes over the bump. So sometimes it bounces, or sometimes it goes over. Then there should be some case in between these two speeds that the solitary wave comes to here and then stays. And then it was case that C is this number. So when the solitary wave has this speed, the solitary wave comes here and then just stay over the bump. Just stand there. Okay, and another case. If lambda is less than this number, now here, this is the critical lambda. If the lambda is less than this one, then because of the bump, the trail of solitary wave will be generated. And the solitary wave comes from left to right, and then this solitary wave will interact the solitary waves generated by this bump. So this is the interaction. The small solitary wave comes from left to the right, and then it interacts here, and then bounces. Because the speed is small. Okay. Now, interaction. Sorry. Okay, so let's see the third movie for that case. The big solitary wave is being generated. The smaller one interacts. And then it bounces. It's just interesting. And the case that the solitary wave comes from right to left is same. So it is from right to left. And if the speed is -1, so the absolute value is now 1, then it bounces. But if C is -2, then it's quite fast, then it goes over. And C is this number, it's critical speed, then solitary wave comes from right to the left, and then it just stays over the bump. And this solution, this stationary wave is same as this one. They should be same as this one. Okay, and there are two cases. The case that two solitary waves comes. The one has smaller speed, and the other has greater speed. So less speed and greater speed. Then the small speed one will be bouncing, and the greater speed one will goes over the bump. Okay, and this is the movie for that case. The faster one goes over, and slower one bounces. Anyhow, long time later, the small stationary solution remains only. All gone. And the small stationary solution, this one, remains. Okay, so this is the part for the theoretical part, and we made some. This is not online anymore. It's already published, and we have made some experiment. For this case. So if lambda is less than some number, then trail of solitary wave appears. and if lambda is greater than some number, then there's no this kind of there's no this kind of phenomenon. So no trail of solitary wave appears. So I went to the Korean Research, the Ocean Research and Development Center, and I asked them whether they can do the experiment with me, and they said okay. So they made some experiments together. The case that epsilon is 1/3 and 1/4. Of course, epsilon, the smaller the epsilon is, the better. But in reality, if the epsilon is too small, then we should pull the bump too quickly, and it's not very easy. So we have checked the case that epsilon is 1/3 and 1/4, and the result was quite similar to the theoretical result. So let me show you that. 아시죠? 딴 데 있으니까 이걸 빠져나가요. We have used the 초고속 camera or high-speed camera, so the shape may not look very nice, but anyhow. Okay, 이게 지금 몇 cm잖아요? So now, some wave appears in front of this ball. 그다음 계속되는 one solitary wave and the other is coming out. So 1, 2, 여기를 갑시다. 여기 1. First one, second solitary wave, and third one is being made now here. Okay, first, second, and third. So 3 trail of solitary waves working. This is a fast video. Slow, please. And slow 갑시다. Slow. 똑같이 80 centimeters. The speed of the bump is 80 centimeters per second. Okay. So now it's a slow video, just slow, same as the last one, but the time is very slow. Bump is now coming here somewhere. It's a slow video, so it will take more time. Down here, yes, here's the bump. Now, instead of making the fluid flow, we pull the bump. Then they are safe. The bump is being pulled with the speed of 80 centimeters per second. And because of this bump, wave is made, and it goes faster than this bump. And one solitary wave is being generated. And here is less compensation. Huh? Bump is being moved now. Instead of fluid flow, the bump is used. Bump is moving. This may remind you of a program in Microsoft. So one is made, and second one is being generated here. So the speed of the solitary wave is faster than the bump. The second one is being made. 이걸 가면은 마지막으로 가죠. And the length of this aquarium is about 20 meters. And we pull the bump 7 meters, 7.5 meters. First one. So this is case that speed is 80 centimeters, so somewhere here. Solitary wave. This is not a sine or cosine curve. You can see the depth of this one is same as depth of this one. So it's a solitary wave. Second wave. And third wave. Okay. 계속 도와주시면 나가서 또 다른. And let us see the case that speed is 98, so it's above critical case, the greater than critical speed. Then there would be no such wave. Now here is the bump. And one wave is being made now. And the wave is just above this bump. It does not go in front of this, ahead of this bump. It just goes with the bump. So it's a stationary. But it's quite wide. It's wider than before. 여기까지만. And this is the case that which one is 1/3. There's no wave ahead of this bump. The stationary wave is moving with the constant speed. Okay. Of course, I made some other pictures, and in fact, there are some more relations. We checked several more cases, but I did not prepare for this talk. There are some other interesting phenomena, and all the experimental phenomena is just consistent with the theoretical phenomena. So we may say the KDB theory is quite good to explain the fluid motion. Of course, quantitatively there will be some difference. But qualitatively they are almost same. So we can conclude that the KDB theory is just good explanation for the fluid motion in the two-dimensional case. Okay, so that's it for today.